Hi students, good evening everyone. Hi students, good evening to everyone. Hope you all can hear me properly and you all can say it properly. Okay, right. So yesterday we were doing the chapter chemical bonding, correct? And with respect to chemical bonding, we did discuss few things. We did start with the hybridization, and I clearly told you that what all is important with respect to the hybridization, correct? I mean, what exactly the hybridization is giving us the idea. That was the main thing, correct? So as I explained you yesterday, that hybridization explains us regarding the geometry of the molecule, correct? When we take some simple molecules, it is very easy to use if we know the hybridization of that molecule, it becomes very easy to predict its geometry, correct? So yesterday we started with the hybridization, its definition, and what are the characters and what are the features of the hybridization. Apart from that, we also tried to study the SP hybridization, correct? So we did the SP hybridization, and also with respect to the hybridization, we tried to solve few of the problems, correct? Now, what another thing we tried to understand yesterday is we tried to understand if it is a carbon molecule or a molecule which is having a carbon, and if we want to find the hybridization of that carbon, it becomes very easy when we understand how many sigma bonds are present for the carbon, because yesterday I clearly told you that sigma bonds are counted for the hybridization because they are formed by the hybrid orbitals, whereas the pi bond, they are not counted for the hybridization because they are formed by the unhybridized orbital, correct? So today we'll continue with this hybridization concept and we will move ahead. Yesterday we did with the SP hybridization, and today we'll try to move to the next part, that is SP2 hybridization. Okay, so in today's class, we are going to move for the SP2 hybridization. Right. Now, when we say SP2 hybridization, so first let us try to understand how do we, start with the SP2 hybridization. So in this SP2 hybridization, there is one s orbital and two p orbitals hybridized to give three hybrid orbitals. Like for example, let me take some example. Okay, so let me say there is a BCl3 molecule. So I'm going to take this particular example here. Okay, so let me take an example of a BCl3 molecule. So if I take a BCl3 molecule, I want to find out what, so let me say I want to find out the hybridization of which molecule here, I mean which species there, BCl3, and I want to find out the hybridization with respect to the boron atom here. Okay, so now, and I want to find out the hybridization of the boron atom, the first thing is I'm going to write the electronic configuration. So I understand that boron atomic number is what? Boron atomic number is 5. So the electronic configuration is going to be what? 1s2, then it is 2s2, then we have the 2p1 configuration, correct? So this is our electronic configuration. So what I clearly understand is when you look at this arrangement of the electrons in the orbitals, so I clearly understand that we find here there are two electrons and we find here there's one single electron. So what exactly will happen now? We have also understood yesterday that half filled orbitals, correct? So here you see there is a fully filled orbital, okay? And let us not forget that this is our valence orbitals. So half filled orbitals, they participate in the bond formation, correct? So there will be what? There will be promotion of the electron, and once this promotion of the electron goes to the, I mean the electron goes to the 2p orbital, the configuration changes, correct? The configuration changes to 2s1 and it changes to 2p2. So here now we have the single electron, and here in this particular orbital we have what? We have two single electrons. Okay, so what exactly is happening now? One s orbital, so you can say that there is one s orbital, okay, and two p orbitals So here you find, so let me say this is my 2s orbital and these are my 2p orbitals. So one 2s orbital and two 2p orbitals, they combine in such a way that they are forming what? They are forming an sp2 hybrid orbital, which you can see here. So they are forming an sp2 hybrid orbital. And what is the geometry of this molecule? The molecule is having a trigonal planar. So even if I try to connect this particular molecule, so here you will try to understand that this is having a trigonal planar geometry. Correct? So once this sp2 hybrid orbital is formed, next what exactly will happen? The Cl atoms, okay, the Cl is going to link over here. So there's one linkage of the Cl, there's another linkage of the Cl over here, and there's another linkage of the Cl over here. So I can clearly show where all the Cls are linked. So let me say here one Cl is linked, and then one Cl is linked over here, and one Cl is linked over here. Okay, so which are the orbitals involved? 1s and 2p orbitals. Hence the hybridization is what? Hence the hybridization is sp2 hybridization. Okay, so what are the things we have to write down here? This is an sp2 hybridization, and then we have a trigonal planar geometry. Correct? So we have a trigonal planar geometry. All the sp2 species will have a trigonal planar geometry. Then the next thing, so if we assume, so let me say I'm going to draw it like this. So let me say the molecule is like this. So this is our geometry here. Okay, so if we try to take the geometry like this, what should be the bond angle here? So if I want to mention the bond angle is going to be how much here? The bond angle is going to be 120 degree. Okay, so you can also write here the hybrid orbital, the bond angles are what? It is 120 degrees. So these are the three main points we have to make a note here. Okay, the angle is 120 degree, sp2 hybridization, trigonal planar geometry. Okay, now let us try to understand it with respect to a carbon molecule. Okay, so let me say a carbon, an sp2 carbon. Okay, so let us think about the sp2 carbon over here. Okay, so now when I say carbon, I'm going to first write down the electronic configuration. So let me say I'm going to write the electronic configuration of a carbon. So here I will write it as 1s2, I write it as 2s2, and I write the electronic configuration as 2p2. I clearly understand this is what? This is my ground state. So one of the electron undergoes a promotion. So the configuration changes to 2s1 and 2p3. So I clearly understand now there's one electron in the 2s orbital and there are three electrons in the 2p orbital. So one here, and one over here. Okay, one over here. So now when all we can say that a carbon is sp2 hybridized. So that is again very important thing. Okay, so let me say now a carbon is present, and now let me say he has made one sigma bond, there's another sigma bond, there is another sigma bond, and now along with that there's also a pi bond. Okay, so I am assuming that here it is a sigma bond, here it is a sigma bond, here it is a sigma bond, but there is one pi bond. Now I clearly understand pi bond is formed by what? Pi bond is formed by unhybridized orbital, correct? The pi bond is formed by unhybridized orbital. So what do I see here? Now how many sigma bonds? 3 sigma bonds. So let me say here it is linked with the carbon. I'm just writing it as a carbon over here. So one hydrogen linked over here, another hydrogen is linked over here. These two orbitals are linked with the carbon. In that, what exactly we are doing, what exactly we understand? So here is our sigma bond, here is our sigma bond. One of them is a sigma bond, the other one is a pi bond, which is formed by the unhybridized orbital. So how many orbitals I'm supposed to calculate, I'm supposed to consider for the hybridization here? 1s and 2p orbitals, correct? One s orbital and 2p orbital. So whenever a carbon is having one pi bond, or I can say it belongs to a category of what? It belongs to a category of alkene. The carbon is said to be what? The carbon is said to be now sp2 hybridized. The carbon is said to be sp2 hybridized. And this sp2 hybrid carbon, will have a trigonal planar geometry. You can see over here, will have a trigonal planar geometry with a bond angle how much? With a bond angle of 120 degree. Okay. Now, with respect to carbon, there is one interesting species over there. Okay. So that interesting species is what? The interesting species, we normally call it as a carbocation. Okay. Carbocation. So the word itself is telling you that a carbon is having which charge? A carbon is having a positive charge because it's a carbocation, correct? That means what? Carbocation is an electron deficient species, correct? So I can simply say that this guy is an electron deficient species. I'm just making a point there. So it is an electron deficient species. Electron deficient species. So what exactly happens here? Again, I'm going to consider the carbon's excited state. So let me say I'm going to write the excited state carbon over here. So when I say my carbon is in excited state, what is the configuration? The configuration is 2s1, and I understand here it is 2p3. So here there is a single electron, and here you will find there are 3 electrons over here. Okay. Now it's an electron deficient species, correct? So what exactly do I mean by electron deficient species? That carbon has actually lost 1 electron. So I'm going to eliminate an electron from the last orbital here. Okay. So you can see that it is an electron deficient species now. It has lost electron. So here you will find there's an empty orbital, correct? So here you're going to find an empty orbital. So when you find an empty orbital, it clearly understands, I mean, we clearly understand there's a loss of electron. So if I say there is a carbon linked with 3 hydrogens. So let me say the carbon is linked with 3 hydrogens, and remember he has also lost an electron, correct? If he has also lost an electron and the name itself is telling that it's a cation, so he will have which charge here? He will have a positive charge. He is going to have a positive charge. So now, if this is the case, just check here. Here there's 1 hydrogen linked. Here there is 1 more hydrogen linked. Here there is 1 more hydrogen linked. That means 1 s orbital and 2 p orbitals are linked to the central. I mean, they are forming an sp2 hybrid carbons, correct? So what do I understand here? The carbocation, what we are seeing over here, the carbocation, what we see over here, which is an electron deficient species, is always which hybridized? It is always again sp2 hybridized. sp2 hybridized. You can see that there is absolutely no electron in the last orbital. Hence, that orbital is not participating in the sigma bond formation or any kind of a bond formation. Correct? As of now, they are not. You see there is no bond formation with respect to that orbital. Okay. So how many orbitals are actually participating? One is the 2s orbital and the 2p orbital. So here you can also change the configuration for the carbocation. Instead of 2p3, you can write it as what here? You can write it as 2p2. Okay. So carbocations are sp2 hybridized, and they are also having which geometry over there? They are also having trigonal planar geometry. Trigonal planar geometry. Okay. So this is all about what? This is all about the sp2 hybridized or sp2 hybridization. Okay. sp2 hybridization. Okay. Let us now move on to the next hybridization, that is our SP3 hybridization. Again, very important, SP3 hybridization. So what exactly happens in SP3 hybridization? You can see in the SP3 hybridization, there is 1 s orbital and 3 p orbitals. They undergo hybridization to give how many hybrid orbitals there? 4 hybrid orbitals. And what are those 4 hybrid orbitals called as? They are called as sp3 hybrid orbitals. And if you can see this structure, it is forming us a tetrahedral structure. Okay, a tetrahedral structure. And this sp3 hybridization, it depends from molecule to molecule, because it depends like how many lone pairs are there and how many, I mean, sigma bonds are there. So all those things matter here. There are different examples showing you the sp3 hybridization, but the shape of the molecules goes on changing. Okay, so let us take some of the examples over here. Okay, so let us try to understand some of the examples. Now, first example, what I'm going to do is I'm going to take an example of a methane guy. I'm going to first take an example of a methane. So when I take an example of a methane, again, what is the formula of a methane? It is CH4. So I clearly understand that the carbon is linked with how many hydrogens? The carbon is linked with 4 hydrogens, as you can see it on the screen here. Okay, the carbon is linked with the 4 hydrogens, the methane structure. So now, when I write the excited state, I clearly understand. Directly, I'm going to write the excited state. I clearly understand. Here is 2s1, and here we have a 2p3. So there's one electron over here, and then there are 3 electrons over here, one here, one over here, one over here. So how many hydrogens are linked now? There are 4 hydrogens, one over here, one over here, one over here, and one over here. So this carbon has involved its 2s orbital, okay, one 2s orbital and 3 2p orbitals. So the hybridization is what here now? The hybridization is SP3 hybridization, giving us what? Giving us the tetrahedral structure. Okay, giving us the tetrahedral structure. And when you see the structure, the following structure over here, you can imagine how exactly the structure looks in a 3D. Okay, how exactly the structure is looking in the 3D. Okay. Now, let us try to discuss this SP3 hybridization with respect to different molecules now. So here you see that a carbon species which has no lone pair of electrons. Okay, so that's a very important point. A carbon has no lone pair of electrons. It forms a regular tetrahedral structure. So here you see there is a regular tetrahedral structure. Okay, no lone pair of electrons on carbon. I can write here no lone pair of electrons on carbon, because you see that all the electrons are involved in a proper bonding. Okay, but when we take some other examples, okay, instead of a methane, so let me say, let me take an example of an ammonia over here. Okay, let me take an example of an ammonia. So now when I write the electronic configuration of an ammonia, okay, so I understand it is 1s2, then you have a 2s2, then you have what? Then you have a 2p3 configuration. So here what exactly happens? 2 electrons over here, then you have how many here? In this particular orbital, there are 3 electrons. Okay, see, you simply cannot promote the electron. For the promotion of electron, it is very, very important that there has to be an empty orbital. Okay, so if there is no empty orbital, you cannot simply promote an electron. Okay, so here promotion of the electron is not possible because there is no empty orbital. So what exactly is going to happen now? We see that one hydrogen is linked over here, one hydrogen is linked over here, and we see one hydrogen is linked over here. That means all my 3 p orbitals, which are those 3 p orbitals, the px guy, the py guy, and the pz guy, all these 3 orbitals are involved in a sigma bond formation, because these are what? These are my sigma bonds over here. Okay, now what exactly the s orbital electrons are doing? Now these s orbital electrons, okay, these are normally known as what? These are normally known as our lone pair of electrons here. So these are normally known as what? The lone pair of electrons. Now, what is this lone pair of electrons doing here? So if we go back to our valence shell electron pair theory, or we can say VSEPR theory, the lone pair of electrons are what? They are contributing. So I can say these are contributing for the stable structure. Contributing for the stable structure, because a molecule will form a stable structure having least repulsions, correct? So the lone pair of electrons, they are having a repulsions, and because of that, what happens? The whole molecule geometry changes and it gives a proper stable structure. So any electrons which contribute for the stable structure, they will be counted for what? They will be counted for the hybridization. So the electrons which are present here, the s electrons and the 3p electrons, all of them are included. Hence the hybridization will be what? Hence the hybridization will be sp3 over here. Okay, so now what exactly has to be the geometry? Okay, what exactly has to be the geometry? So nitrogen sits in the center. Then you have a lone pair of electrons over here. So let me draw the lobe over here. So this is your lone pair of electrons. Then we have an hydrogen over here. We have an hydrogen over here, and we have an hydrogen over here. Okay, so the overall geometry, if I speak about the overall geometry. Now, what is this overall geometry? Why do I use this overall? Because the overall will include what? The overall will include the atoms as well as the lone pair of electrons. Okay, so the overall geometry will include the atoms as well as the lone pair of electrons. So if I try to connect this particular structure over here, I clearly understand that this has generated what? This has generated the tetrahedral structure. So it has generated the tetrahedral geometry. Tetrahedral geometry. Okay, but now if I try to speak regarding the atoms only, the geometry with respect to only the atoms. Okay, so if I try to connect it, so just check how do I connect it. So let me say here I connect it over here, then I connect it over here, then I connect it over here, then I connect it over here, and let me say it is like this. Okay, so what do I see here? I see it's a pyramidal structure. Okay, so geometry will be what here now? Geometry with respect to atoms, it is going to be what? It is going to be a pyramidal structure. Pyramidal geometry over here. Okay, so what do I understand is, I'm going to repeat it once again. I'm going to repeat it. When we consider the overall geometry, including the electrons also, the overall geometry is tetrahedral, no doubt in it. But when we consider only the atoms, okay, when we consider only the atoms, look at that. What is the geometry there? The geometry is pyramidal structure. Okay, and the bond angles are very, very important. Okay, so I am going to mention the bond angles here. So if we have a normal structure, so just give me 1 minute. So if we have a normal tetrahedral structure, like for example the methane structure, what you see over here. Okay, when you see this methane structure, the bond angle over here with respect to what? With respect to the methane, it is 109.5 degrees. So please make a note. Normal tetrahedral structure, it is 109.5 degrees. But the previous structure, what we came across, the ammonia guy, correct? The previous structure, what we came across with the lone pair of electrons, which was present over here. Okay, the bond angle, okay, the bond angle is 107 degrees. Please make a note. Bond angles are very, very important. So if you check your state exams or when you check your CET level exams, you will definitely come across questions on the bond angles also. Bond angles. Okay. most of the times we also come across few confusions. Okay, what is that? Students keep asking that when you see this structure, okay, when you see this particular structure, the green structure over here, student asks that, sir, which is s orbital, which is p orbital, which is px, py? No, all of these are what here? All of these are actually sp3 hybrid orbitals. So even this is sp3, even this is sp3, because the s orbital and the 3p orbitals along the x-axis, z-axis, and the y-axis, they have combined to form a new orbital. And what is this new hybrid orbital? All those orbitals are sp3 hybrid orbitals only. sp3 hybrid orbitals. Okay, so this is with respect to ammonia, and we have also spoken about with respect to what? With respect to methane. Now there is one more sp3 structure. And which is that one more sp3 structure? That is H2O, a water molecule. Okay, so this guy is also what? This guy is also an sp3 structure over there. Okay, so now let us try to understand how exactly this guy becomes an sp3 and what is the bond angle. Now, from our lower standards, I think we all remember that water is having a bent structure, correct? Water has a bent structure, and if you remember the representation, we write a hydrogen over here and a hydrogen over here. So let us try to understand now. So this is my oxygen, atomic number 8. Then we have an 1s2, then we have a 2s2, then we have 2p4. So valence orbitals, we see 2 electrons over here, and even here in this case, we see there are 2 electrons over here, 1 electron and 1 electron. correct? So how many half-filled orbitals do we see? 2 half-filled orbitals. And one more thing, what do I understand? I understand that these two are our lone pairs. These two are our lone pairs, correct? Now, if we try to observe how exactly the bonding takes place, one hydrogen is linked over here, another hydrogen is linked over here. Now, as we have already studied that lone pairs are doing what here now? Lone pairs are contributing, correct? Lone pairs are contributing for stable structure. This we have already studied, correct? Lone pairs are contributing for the stable structure. So definitely they are counted in what? They are counted in the hybridization. So what do I understand here is one s orbital and 3 p orbitals are considered for hybridization, and the whole thing will be what now? It is sp3 hybridized. That means the oxygen what we see here is sp3 hybridized. Now, where exactly are the lone pairs present? The lone pairs, one of them will be sitting over here and another one will be sitting over here. So if you want me to write a proper structure, give me just 1 minute. So let me say I write the oxygen over here. So one lone pair, I'm going to write it like this. So let me say the lobe of one lone pair. Then let me say I'm going to write the lobe of another lone pair over here. Okay, this is the lone pair. Then let me say there's an hydrogen, and let me say now there's an hydrogen. Okay, so this is exactly how. So even if I try to connect the points, so even if I try to connect the points, I clearly understand that this guy is what now? This guy is having overall geometry is going to be what? Overall geometry is going to be tetrahedral. Overall geometry is tetrahedral, correct? Overall geometry is tetrahedral. Okay, but when I say the geometry with respect to only the atoms now, when I say geometry with respect to only the atoms, then what exactly is going to happen now? Here we see that this guy is having a bent structure. Okay, so this guy is having a bent structure over here. The bent structure. Okay, the bond angle in the H2O molecule, we have come across a methane, bond angle was 109.5 degrees. We have come across the ammonia 107, and here the bond angle is going to be what? 104.55 degrees. 104.55 degrees. So what do I understand is, with respect to SP3 hybridization, SP3 hybridization, when we take the CH4 species, so I'm speaking about the bond angles, okay? The bond angles is what I'm going to speak about. When we take the bond angles, okay, my CH4 is having a larger bond angle, then comes the NH3, and the last one is what? Last one is H2. It's a very important thing, so only I'm giving you people. Okay, bond angles of each species over there. 109, 107, 104. So this is how the decreasing order of the bond angle. So normally we call it as what? Normally we say it is a V-shaped or bent structure. So even if you see somewhere written V-shaped, I think we should not be V-shaped, or even angular is what they are using. So either V-shape or bent or angular, it's all fine for the H2O molecule. The only thing is all these three are sp3 hybridized with different bond angles. Different bond angles. Okay. Now we are done with what? Now we are done with sp, we are done with sp2, and we are also done with the sp3 hybridization. Okay. Now let us move on for the further studies. Now we will start with what? We will start with SP3D hybridization. We'll move on towards the SP3D hybridization. SP3D. SP3D hybridization. Okay. Now, when we speak about the SP3D hybridization, so what do we understand? The first thing we understand over here is there is an involvement. Just check the type of orbitals that are involved. Okay, or from where exactly it is involved, which orbitals the hybridization starts. So here you see there is a 3s orbital. Here you see there is a 3px orbital. Then you see there is a 3py orbital. Here you see that there's a 3p z orbital. Okay, and the most important thing, because it is just not important that it's an sp3d, sp3d2 or sp3d3 hybridization. Not only that, it is also very important to know among the 5d orbitals, which orbital is actually involved in the hybridization. So now when you check the sp3d hybridization, you will find that here 3dz square, okay, 3dz square orbital is involved in what? It is involved in the hybridization because it is present along which axis? It is present along the z axis. So that is very, very important. So what exactly is happening now? One 3s orbital, 3p orbital, and one 3d orbital. So you have to also understand that they all belong to a principal shell of n is equal to 3, correct? So there is not huge difference in their energy level. There's only slight difference in the energy level. That was the basic condition, correct? Slight difference in the energy levels. They will combine and they are going to form an hybrid orbital. So you will see that all these orbitals, they will combine to produce which hybridization now here? They are going to produce SP3D hybridization. SP3D hybridization. Obviously, I am going to take an example and explain it. So let's not worry about it. Okay, SP3D hybridization. Now, what exactly is the shape of this SP3 hybridization? Just check the shape of this SP3 hybridization. Okay, so I clearly understand if my first let me take an example. Okay, let me try to explain it with an example. So I'm going to take an example of, let me say, PCl5 structure. Okay, so let me say I'm going to take a PCl5. So just check how do I arrive at an SP3D hybridization now. Okay, and I will also explain you what is the geometry. So when you take a PCl5 structure, okay, so I understand my P, whose atomic number is what here? Whose atomic number is 1515. I'll start writing the electronic configuration. So neon starts from here, then you have a 3s orbital, then you have a 3p orbital. So 15 means what? 3s2 and 3p3, because let us not forget they all belong to nitrogen family, correct? So the valence electrons are absolutely same. So 3s2 and what? 3s2 and 3p3 configuration. Okay, so the only thing, I mean, the other thing we should not forget is here there is also 3d0 present, correct? So we also have a 3d0. Just give me 1 minute. I'm going to take another page. Yes, so we are also having what? We are also having a 3d0. So I'm going to write it from here. So we have a neon, okay, a neon with 3s2, then we have a 3p3, then we have a 3d0. Okay, so we see now here there are 2 electrons. We see here there are how many electrons? 3 orbitals with single electron in each orbital. Then with respect to D, we have 5 orbitals. Okay, so you see that the entire d orbital is what? As of now, the entire d orbital is actually empty over there. Okay, so now what exactly happens when you check? So we were trying to explain the PCl5 structure, correct? We were trying to understand the PCl5 structure. So if you check this particular configuration, I clearly understand half filled orbitals are how much? 3. So one Cl will attach, one more Cl will attach, one more Cl will attach. So according to this configuration, only 3 chlorines can attach. But we want how many? We want 5 chlorines to be attached. So to accommodate the 5 chlorines, the promotion of the electron take place now. So the electron from the 2s orbital, is going to shift to which orbital now? It is going to shift to the 3d orbital. Once it promotion of the electron takes place from 3s to 3d, the configuration changes to what? Here it becomes 3s1. Then we have a 3p3 here. Then we have a 3d1 configuration. That means here you will see there is a single electron. Then here we are seeing there are 3 electrons. Okay, and here we see there are 1, 2, 3, 4, and 5. You'll see here there's a 1 single electron. Okay, so how many now? Totally 5 half filled orbitals is what we come across. So now what exactly happens? one Cl links over here, another Cl links over here. You will see there's one more Cl linking. There's another Cl and there's another Cl. So one 3s orbital, three 3p orbital, and one d orbital gives us which hybridization here? SP3 and a D hybridization. SP3 and D hybridization. That means one s orbital, three p orbitals, and one d orbital of the phosphor is involved, and hence what is going to happen? They are producing a new hybrid orbital called sp3 hybrid orbitals. Okay, now let us think about the structure. What exactly happens with respect to structure now? Okay, so we have to think about what? We have to think about the structure. So phosphorus sit in the center. So let me go back to this particular thing here. Okay, so now just check here. What exactly is happening? The phosphorus is sitting exactly in the center. Okay, so you will see the phosphorus sitting exactly in the center. Then the Cl over here, one more Cl over here, one more Cl here, one more Cl here, and one more Cl over here. Okay, so 5 Cls are connected. So if I want to connect this structure, so if you see here in the center, you will see there is a trigonal structure, correct? In the center, you will see there is a trigonal structure. But the main thing what we have to observe is, look at the structure. You will find a pyramid on top. Hope you all can get the pyramid. You will find the pyramid on top of it. Okay, you will also find a pyramid at the bottom. So if you try to understand the structure, so yes, you will also find a pyramid at the bottom, correct? So how many pyramids it is having? It is having two pyramids. So I understand that this guy is what now? It is bipyramidal. First thing, it is bipyramidal. You will find a pyramid on top, and you will also find a pyramid at the bottom. It's a bipyramid. The next thing is the pyramid containing how many faces? So I clearly understand that it is having three faces, right? 1, 2, and the behind one is 3. So I understand that this guy is what? This guy is trigonal bipyramidal geometry. Trigonal bipyramidal geometry. Trigonal bipyramidal geometry. Trigonal bipyramidal. Okay, now when we speak about this trigonal bipyramidal geometry, so let me draw the structure now. So let me say this is my P. You will see there is a Cl here, you will see there is a Cl over here, and you will see there is a Cl over here. Okay, and I clearly understand on exactly the top, okay, there is a Cl, and at the bottom also there is a Cl. Now what is the difference in the writing? What difference do you see here? Okay, check the bond length. Check the bond length. Okay, check the bond length. So you should check the bond length over here. Okay, and also check the bond length over here. You will find that there is a difference in the bond length, correct? There is a definitely difference in the bond length. Okay, now these bonds which I have written on top, or you can say which I have written from the red pens. Okay, now these bonds are called as what? These bonds are called as axial bonds. So this guy is now the axial bond, and here also you will find that there is an axial bond. Okay, so these are your axial bonds. So even on top you will find there is an axial bonds. Okay, the three which I have written with the black, they are called as what? They are normally known as equatorial bonds. Equatorial bonds. And what I do understand here is, when it comes to the length, okay, when it comes to the length, I clearly understand that my axial bonds are longer than what? Longer than the equatorial bonds. Axial bonds are longer than equatorial bonds. So please make a note of it. Okay, so if I have to write it, in terms of picometer, normally axial bonds are how much? Normally the axial bonds are, in this case, 209 picometer. So 219, not 209, it is 219 picometer. So you can make a point there. 219 picometer. And when it comes to the equatorial bonds, it is around 204 picometer. It is around 204 picometer. So here it is 219 picometer. So you will see that when we see a structure of a trigonal bipyramidal geometry, the geometry itself is having two types of bonds. One is the axial bond, the other one is what? The other one is equatorial bonds, axial and equatorial. And I clearly understand that the bond length of the axial and equatorial is not exactly same. It is absolutely not same. I clearly understand my axial bonds are much larger compared to what? Compared to the equatorial bonds. Now, one homework question you have to take here is the homework question. Why axial bonds are longer compared to the equatorial bonds? Please write down the homework question. Why axial bonds are longer compared to the equatorial bonds? Axial bonds are longer compared to the equatorial bonds. Okay, first thing. Next, let us now discuss about the bond angles. That's again a very important thing. Okay, let us now try to discuss about the bond angles. So if you see the bond angles with respect to the trigonal pyramid, I mean the trigonal geometry which is present at the center, here the bond angle has to be what? The bond angle has to be 120 degree, correct? The bond angle has to be 120 degree. But when you take the other bond angle, so let me write it. When you take the other bond angle, so let me say I'm going to mention the bond angle which is present over here. Okay, so when you take the other bond angle, this bond angle when you take, or with respect to here, or with respect to here, okay, or from the bottom side, the bond angle is how much? The bond angle is 90 degree. The bond angle is 90 degree. So I clearly understand that for a trigonal bipyramidal structure, between the trigonal part, you will find the bond angle is how much? 120. But between the axial and the equatorial bond, the bond angle is 90. Bond angle is 90. Bond angle is 90. Okay. So this is all about what? This is all about SP3D hybridization. SP3D hybridization. Okay. Now, let us move on to the next one. The next one is SP3D2 hybridization. SP3D2 hybridization. Okay. So I clearly understand. Let us not forget that which d orbital was involved over here. The d orbital involved over here was dz square, 3d z square orbital. Okay, 3d z square orbital, because you will also see that the chlorine here, the axial bonds, what you see, they are actually along the z axis, correct? So that in that axis, the d orbitals are actually involved. Okay. Now let us come to what? Let us now come to the SP3D2 hybridization. SP3D2 hybridization. So in the SP3D2 hybridization, what do I understand here? In the SP3D2 hybridization, there is an s orbital involvement. There is 3 p orbitals involvement. Obviously, when I say 3 p orbitals, it has to be one along the x-axis, y-axis, and another along the z-axis, correct? These are the only 3 p orbitals. The other thing we have to understand here is there is again an involvement of a dz square orbital, and along with that there's always also an involvement of the dx square minus y square orbital. Okay, so we have to understand the d orbitals what are mentioned over here, they all are along what? Along the axis. So they all are along the axis. So when I say x-axis, y-axis, and the z-axis, so they all are along the x-axis, y-axis. I mean the x square minus y square, d orbital is along the x-axis and y-axis. The dz square is along the z-axis. So that is what it is trying to say. Okay. Now let us take a simple example over here. Okay. Let us try a simple example. So let me say I am going to take an example of an SF6 molecule. Okay. So let us take an example of an SF6 molecule. So when I take an SF6 example, the first thing is what I need to write the electronic configuration, correct? So here it is going to be what? Neon. Then I have a 3s2, then I have a 3p4. Remember, he belongs to the oxygen group family, correct? And let us not forget that there is again here a 3d0. Okay. Again, I find there is a 3d0. Clear? Now, it's a 3d0 structure. So what exactly is happening now? Here you will find the 3s2 with a 2 electron. Then you find the 3p3, I mean 3p4, sorry, 3p4, 2 electrons, single electron, single, and then there are 5 d orbitals. Okay, so here you will see there's a 3d0. So what exactly should happen now? If you watch this particular structure, I mean the configuration, how many fluorides, I mean how many fluorine atoms can be accommodated? Only 2. But how many are present here? 6 are present, correct? So promotion of electrons should definitely take place. So promotion of electron will take place. Look at the promotion of the electrons now. So I'm going to promote the electron. So one electron shifts over here. The promotion is possible because of the empty d orbitals. Okay. And also you see there's a promotion over here. Okay. So you'll see the promotion. So once this promotion takes place, the configuration completely changes. It changes to 3s1. It changes to 3p3 and it changes to 3d2. So here you will find that there is one electron, and in the p set you will find there are 3 electrons, and in the d set 1, 2, 3, 4, 5. So you will find here there are 2. Okay. So how many half-filled orbitals have been generated here? There are 6 half-filled orbitals generated, correct? So if there are 6 half-filled orbitals generated, so now they can have how many bonds over, I mean, how many fluorines can be accommodated? 6. 1, 2, then you will find the 3, then you will find the 4th one, then you will find the 5th one, then you will find the 6th one. And remember that this guy is actually a z square and this guy is x square minus y square orbital over here. Okay, so that is a very important thing to understand. So this is how the hybridization is produced. SP3D2 hybridization, 1 s orbital, 3 p orbitals and 2 d orbitals. So the hybridization is giving what? It is giving us the SP3D2 hybridization. Okay, now let us try to understand regarding the geometry of the molecule. Okay, so how exactly is the geometry? So if I write a sulfur over here, then I'm going to write a fluorine, then you will find a fluorine here, then you will find a fluorine over here, then you will find a fluorine over here. Now one fluorine I'm going to connect it on top and the other fluorine I'm going to connect it at the bottom. Okay, now if you try to imagine the structure in a 3D, that would be super. So if you try to imagine the structure in a 3D, okay, so if I want to connect this guy, so what exactly is going to produce now? It is definitely producing me an octahedral geometry. So you will see now there is an octahedral geometry structure. Okay, so just give me 1 minute. I'm just trying to connect it. Right. So yeah. Yes. So it is trying to produce what here? It is trying to produce an octahedral geometry. So please make a point, octahedral geometry, octahedral structure, octahedral structure, octahedral structure. Now, let us try to understand. So once we are done with this octahedral structure, let us now try to understand. Octahedral structure is over. Let us now try to understand what is the bond angle in it. Okay. So next thing is what is the bond angle. So I'll give you exactly some 40 seconds. So just try to understand what is the bond angle, and your time starts now. The bond angle. Okay. Bond angles. Right. Now, when you see the bond angle over here, so I'm just going to write it like this. So let me say I have a sulfur, let me say I have a fluorine, and let me say I have a fluorine, and the other structure over like this, correct? The other structure over like this. So what do I understand over here is, what do I if I say now these are my axial bonds and the other things are the equatorial bonds, the bond angle between them is going to be what? It is going to be 90 degrees. Correct? The bond angle is going to be how much? The bond angle is going to be 90 degree. Now I'll give you again a 30 seconds. Try to tell me what is the bond angle between the equatorial bonds. Now this angle is between what? This angle is between the axial and the equatorial, correct? So what I have written here is between the axial and the equatorial. So my question is, Now tell me, what is the bond angle between the axial bonds? 30 seconds is what you're having. 30 seconds. How many 90 degrees you're having? That is the most important question, correct? How many 90 degrees angle you're having? Okay. So how exactly the questions can come here? Okay. So the questions can come, how many 90 degrees? Okay. How many 90-degree bond angles? How many 90-degree bond angles? So the question normally comes comparing, referring with an example of octahedral or your trigonal bipyramidal, okay, square pyramidal structures like that. They give on. Okay, so you have to identify what exactly is the bond angles, okay, or how many 90-degree bond angles are possible. Clear? So this is all about what? This is all about the SP3D2 hybridization. I repeat, this is all about what? This is all about the SP3D2 hybridization. Okay. Now there's one more hybridization, which is SP3D3 hybridization. SP3D3 hybridization. So that will be your homework. I can also give you an example which molecules normally form the SP3D3 hybridization. So I'll just give me just 1 minute. Yeah. So SP3D3 hybridization. SP3D3 hybridization. So if you take an example of an IF7 molecule, okay, if you take an example of an IF7 molecule, so the homework is what? You have to identify what is the hybridization of an iodine, how exactly the promotion of the electrons takes place. Okay, then you have to understand what is its structure, I mean to say what is its geometry, and also identify what are their bond angles. What are their bond angles? So this will be what? This will be the homework part of the class. Okay, right. So let us now try to solve one or two problems. Okay, right. So as usual, I will always give you 30 seconds to solve, and your time starts now. You have 30 seconds to solve this problem. In which of the following pairs the two species are not isostructural? So you find there is new word here. Okay, we have already come across isoelectronic, correct? We have come across isoelectronic. Now we are coming across isostructural. That means what? Isostructural means same structures, or I should say same geometry. Which of the following molecules? So the question is what? Which of the following molecules do not have same geometry is what we need to find. Okay. Now, what are the possibilities we have to check? We have to check the hybridization. Okay. So the chances are what? If there is same hybridization, then there can be same geometry, correct? If we have a same hybridization, then there's every chance that there's a same geometry. Correct? That is the first important thing. So now let us try to understand the hybridization of all the things. When you take the CO3 2 minus, what is the structure? One by one, I'm going to write. So this is my CO3 2 minus structure. So here there's an oxygen, here there's an oxygen, negative charge and a negative charge. This is my CO3 2 minus structure. Nitrogen, double bond oxygen, coordinate bond oxygen. Then you have oxygen with the negative charge. Oxygen with the negative charge. Now check the hybridization. What should be the hybridization with respect to these molecules now? Okay, so here I find a sigma bond, one is the pi bond, another one is sigma bond, correct? You find a pi bond, sigma bond, and you also find a sigma bond over here, correct? So I clearly understand that they are sp2 hybridized, and I clearly understand that both of them, they possesses a trigonal pyramidal structure, or trigonal planar structure, correct? Not pyramidal, trigonal planar structure. That means what? These two are here isostructural. These two are isostructural. Isostructural geometry. Isostructural geometry. Okay. Now let us go to the next structure, the PCl4 and SiCl4. Okay. PCl4. So I'm just going to add one more page. Give me just 1 minute. The PCl4 and the Yes. So let us go to the next one, the PCl4 and the SiCl4. So if you check the PCl4, so you will find there's one Cl over here. You'll find there's one Cl, you will find there's one Cl, there's one Cl, and the whole thing is having a positive charge. Okay. The SiCl4 will also have a similar structure. SiCl4 will also have a similar structure. What is the reason? Because the reason is they are having the same hybridization. Okay. So again, you will find that these are what? These are isostructural with each other. So these are isostructural with each other. Okay. PCl4 and SiCl4. Now let us try to understand the PF5 and BRF5. Okay. PF5 and BRF5. PF5 we have just discussed, correct? So here you find a fluorine, here you find a fluorine, then here you find a fluorine, then you find a fluorine over here, and you find a fluorine over here. So I clearly understand this guy is what? This guy is trigonal bipyramidal, correct? This is going to be trigonal bipyramidal structure. Trigonal bipyramidal structure, correct? But when you see the BRF5 structure, BR, if I write the Lewis dot structure BR, so if we identify the Lewis dot structure, here it is having 7 electrons on it. So BRF5, correct? BRF5 means I'll attach one fluorine. Let me attach another fluorine. I'm just first randomly attaching another fluorine, then another fluorine, then another fluorine, correct? So I clearly understand there are 5 fluorines attached and there is one lone pair. So here is going to be what now? Let me say this is my BR. Okay. So now let me say there's one fluorine attached here, one fluorine attached here. Let me say one fluorine attached here, another fluorine attached over here, and I'll keep the lone pair of electrons over here. Okay. So these are my lone pair of electrons, and let me say one fluorine is attached over here. Okay. So here I got what? Here I got trigonal bipyramidal structure. Correct. But now when I see this particular thing, I clearly understand that this guy is square pyramidal structure. Correct? BRFI is forming what? It is forming a square pyramidal structure. Square pyramidal structure. It is forming a square pyramidal structure. So what do I understand now? My PF5 and BRF5 are not isostructural. So you can make a point there. These guys are not isostructural. Not isostructural. Okay. So the thing is what? These two. Okay. So even here, if you find this guy has to be what? This guy has to be an SP3D2 hybridization. This guy is also an SP3D2 hybridization. Correct. So when they are SP3D2 hybridization, there's every chance that they can have what? They can have an octahedral geometry. So the fourth option, both of them are having an octahedral geometry. So they are what? They are isostructural species. Okay. So the C option is not isostructural. So similar set of questions is what you're going to get in your NEET paper. Similar set of questions. Okay. Right. So if you have any doubts, please let me know. If you have any doubts, please let me know, or else let us stop the class. Thank you so much.